All right, guys, we are going over function analysis, and I went ahead. This table is completely empty in your OneNote and in your Desmos, but I filled it out here. And this is kind of the calculus explanation that they're looking for when we're asking about all these key features of a function. So we know that function f is increasing when f prime is greater than 0. That means our derivative is positive, and then it's decreasing when our derivative is less than 0. And if you think about it, that makes sense because derivative is slope. And then we have relative maximums and mins when that first derivative changes from positive to negative. So just kind of as a reminder, if you had f prime of x, and let's say I had factored and done all the things, and I got x squared, and then I got an x plus 3, you have two solutions here, right? You have a 0 and a negative 3. This 0 is not going to be a max or min because it has a double multiplicity, which means that that function is bouncing, right? It's not changing signs at that point. So if we were to think about that, just following through, you would have that negative 3 and that 0 as solutions. And this is cubic and positive. So the end behavior, it starts low, ends high. It would cross through negative 3 and bounce at 0. You can always make a sign chart, right? And you're like, I'm going to plug in values. Like I'm going to plug in a negative 4 and see that that is a negative. And then I'm going to plug in negative 2 and see that that's a positive. And then a 1 and see that that's a positive. So there's no sign change happening at that 0 either way. So just something to keep in mind. Remember that concavity deals with, so increasing, decreasing, max and mins deal with the first derivative, and then concavity deals with the second derivative. Remember that it is concave up if f double prime is greater than 0, but a point of inflection only happens when that concavity changes. So just like relative mins and max happen when that first derivative changes signs, similar to that second derivative, that point of inflection, so that f double prime has to be changing signs. So let's look at this first question here and kind of go over this together. Just reviewing, this was an FRQ from the 2008 AB exam. Question 5, and this is calculator inactive, which means no calc. So no calc on this one. That's great. We're going to do it by hand. Let G be continuous. So here's G prime. That's super important. Sometimes I write that like really big. We know that g of 2 equals 5, the graph of a piecewise linear function, and the derivative g is shown. So it's piecewise, it's linear, but we also know that it's continuous, which means that we can work with it. So our first question asks us for the x-coordinate of all points of inflection. Now you can go back up to your table and be like, ooh, wait, what's that asking us to do? But I remember points of inflection is talking about the double derivative. So this is f double prime of x changes signs. Or, because I don't have an equation, I also know if I go back up here, I'm like, okay, that's also when f prime is changing from increasing to decreasing or decreasing to increasing, right? Because it's like the slope of the slope. So I see that we're changing signs. We're going from positive to negative. At 1, we are going from decreasing to increasing at 4. So let's get that written down here. So I'm going to say g of x has POIs at x equals 1 and 4 because, remember, we're always using names. We never say it. Oops, not f prime. G prime of x changes from increasing to decreasing or decreasing to increasing. All right, this second one, absolute maximum of g on the interval -3 to 7 with a justification. Now, remember that we always need to check like potential maximums as well as endpoints because my function could start or end higher than where that little relative maximum occurs in the middle. Now, this one's kind of fun because we don't have an equation, so we're actually going to use some integration. This is kind of like a beautiful coupling of just like units 5 and 6 both together, which is really great. So absolute maximum on the interval -3 to 7, I am given the starting point of g sub 2 is 5. Now, if we remember when we talked about that integration and those fundamental theorems of calculus, we said, okay, I know that if I'm looking for g of -3, because I know I'm going to be checking, let's write this out here. I'm going to be checking -3. I'm going to be checking 2 because that's where my derivative goes from positive to negative. And if I think about that on a graph, we're going from increasing to decreasing, that's a maximum. So I'm going to be checking 2. And then I'm going to be checking positive 7 because that's my endpoint. And these other guys here, it looks like -1 and positive 6, those are both minimums because we are going from decreasing to increasing. So we don't have to check those at all. So we know we're checking g of 3. That is going to be, we're going to say g of 2, because that's what we're given, plus the integral from 2 to -3 of g prime of x dx. Now, this is cool here because now you just need to take areas. We all know how to do that. So if we get this done, we know g of 2 is 5. And then from 2 to 3, I'm actually going to flip this integral because this is improper, right? We have that higher value is on the bottom instead of the top. So we're going to say minus, that's the integral from -3 to 2 of g prime of x dx. And then I'm just going to find these two areas, or there's actually kind of like 3 shapes happening here. So we have 1/2 base times height. So 2 times 4 is 8. That's a -4. It's below the x-axis. This next triangle has a base of 2 and a height of 1. So half of that gives me an area of 1. And then we have this cute little area of 0.5. So this guy is going to be 5 minus -4 plus 1 plus 0.5. Get that evaluated pretty quickly here. It is not that bad. And I get that this is going to be 7.5. So there's g of 3. I'm actually going to make myself a little table out here to the side. We're going to move over here to get a little bit more room. So I'm going to say, all right, I know g of 3 is 7.5. Then g of -3. Woo. Then I'm going to check my next guy. So my next one was, what was my next one? 2. G of 2 I'm given. Wow, easy. G of 2 is going to be +5. And then my last one is going to be g of 7. So I know that g of 7 is going to be g of 2 plus the integral from 2 to 7 of g prime of x dx. So that's going to be 5 plus, it's going to be this negative area and this tiny little guy right here. So that triangle has a base 1, 2, 3, 4 and a height of 2. So that's that -4. And then this little booger has a base and height of 1. So that's going to be a plus 1/2. I can already tell that this value is going to be smaller than my g of -3. So I'm going to say absolute max at x equals -3 for g of x on the interval -3 to 7. And you can say because g of -3 equals 7.5. And really, your math is kind of going to be the explanation here. You can like go on and say like, oh, 7.5 is greater than the others, but it's not the end of the world. All right, moving on to part C. Find the average rate of change of g of x over the interval -3 to 7. So for this guy, we are going from, oh, great. We have -3 all the way to +7. We already know what's happening. Because for average rate of change, I'm going to write this down, AROC, we need that original function. So we actually kind of got that help already. We know that that's going to be g of 7 minus g of 3 over 7 minus negative 3, which turns into that 7 plus 3. So then we're just substituting those values that we found earlier when we did that absolute maximum. When I found g of 7, you should have gotten that that was 1.5. G of 3, that was that maximum value, was 7.5. And then this guy is going to be over 10. Remember, you can leave it here, and that's probably preferred. That way you don't mess up with your decimals since you don't have a calculator. You could also say, like, okay, this is 6/10, negative 6/10. And there's another reason why you shouldn't go down all the way, because if I forgot that negative sign, it would have completely changed my answer. So I would just say, stay here. Don't do more than you have to. Find the average rate of change of g prime of x over the interval negative 3, 7. Does the mean value theorem guarantee? All right, remember that mean value theorem talks about slope. So let's get this average rate of change first because it says we need it anyway. Sometimes you read the question and you're like, oh, if I can tell that I can't apply the mean value theorem, I don't have to do it, but it asks for us to find it. So we know that this is going to be, so AROC over the interval negative 3, 7 equals, that's going to be g prime of 7 minus g prime of negative 3 over 7 minus negative 3. We know that that denominator is 10. And then on my function, it looks like that output is 1 at 7, and then at negative 3, it's negative 4. So we're going to say 1 minus negative 4, and then we can leave it like that. Or if you want to do the math, that's fine as well. We would get 5 over 10. Does the mean value theorem guarantee? So mean value theorem talks about slope. Here we have all the slopes that exist over this interval. When I'm looking at this guy right here, it is not, we have cusps, so we don't know about g double prime, right? Because I have a cusp right here, I have a little bit of an edge right here, and I definitely have a cusp down there. So because it is not differentiable, the mean value theorem does not apply. So I'm going to say g prime of x is not differentiable over entire interval, negative 3 to 7, therefore MVT doesn't apply. And that is all you need. You would get a point for that slope and then a point for saying that mean value theorem doesn't apply.